Let's try a couple of our optimization problems, and I wanted this in a video because I think you might need to try them a few times yourself to make them become easier. The first problem is not a difficult one because you've done problems similar to it in both algebra and geometry. So along some existing fence line, we are going to build a rectangular field using 2,400 feet of fencing. So we've got two parallel sides, so if we let those have a length of x feet, then we've used up 2x, so we would have 2,400 minus 2x left for the third side. So we can think about the extreme cases here. It is possible, we already know we wouldn't do it, but we could build a fence where we used all of the 2,400 on these two sides, so we could go up to 1,200 and then this side would have 0. But of course the area then becomes 0 because the rectangle collapses into a segment. And likewise we could make we could make a field that has 0 for its width, and we could use the entire 2,400 as the vertical side. But again, we know we're not going to do that because it would give us an area of 0 square feet. But what it does tell us is that x could go as high as 1,200 feet, and x could be as small as, so x could be as small as 0, or it could be up to 1,200 feet. So we actually know that we've got a domain here for x. So x is going to be somewhere in this interval from 0 to 1,200, from 0 to 2,400. All right. Nope, sorry, 0 to 1,200. It's the x side we're interested in, not that vertical side. Okay, we want to come up with the maximum area using that fence, so we want to come up with an area function. Well, this is pretty simple. We know it's just the base times the height, or length times the width. So we know our area function is 2,400x minus 2x squared, and now we want to maximize. Well, where can the maximum occur? The global maximum can only occur at a critical number or at a closed endpoint. So let's find the derivative in order to find the critical numbers. So as soon as I find the derivative here, I can factor a 4. So we can see that a prime is equal to 0 when x is equal to 600. So that's our only critical number. So now we could do our closed interval test, and we could say, well, let's find the area at the endpoint of 0, or at the critical number, or at the other endpoint of 1,200. And then we could choose the one that is maximum. Or, just to show you that we've got options here, instead of the closed interval test here, we could use the first derivative, the value of the first derivative, since we only have one critical number, which, by the way, if this were a multiple choice question, I would guess that my answer is already 600. But there is, in some cases, you might not know, is 600 going to be a maximum or a minimum? And it only takes a little to convince yourself of that. So let's think about our intervals. When x is between 0 and 600, look at a prime. If we put in a number between 0 and 600, then we can see that a prime of x would be greater than 0. And if we choose any value between 600 and 1,200, we can see that a prime of x will become negative. So we know, because it changes from increasing to decreasing, we know that a of 600, which is going to give us some y coordinate, that's going to be our answer in square feet, is a maximum. And since A only increases and then only decreases, this is a global maximum. Now, you might not even write this last explanation, but I want to make sure that everybody understands that when there is only one critical number, so if the graph is only changing once, then the local maximum must become a global maximum. Okay, then you can grab your calculator and don't put 600 into a prime of x. We know that would turn out to be 0. So that might confuse you. So to find our area, our maximum area, put 600 into your area formula, and you will come up with 720,000 square feet. So that's our maximum area, and we know how to build that. So we could clarify. So the fence should be, or the fenced rectangle should be 600 by, so if we use, let's look at our picture here again, maybe that might help here. If this is 600 for this side and 600 for the top side, then we've used up 1200, so we know that it's going to be 600 by 1200. 600 feet by 1200 feet. Okay, so for sure we've answered the question then. Our next example is quite a bit more complicated, so it takes some time to make sure we understand it. So, we need to get this gentleman across the river, and he needs to go from point A, our starting point at point A, and he needs to get to point B, his ending point. All right, so how can he get across the river? Well, lucky for him, he's got a boat, so he can row across the river, and we know that he can row at 6 kilometers per hour. So, of course, an obvious idea would be for him to get in his boat and row all the way from A to B. So he could, that would be his first option, would be to row all the way from A to B. But he knows that he can actually run faster than he can row. So that's not his only option. So another possibility would be for him to, instead of rowing directly from A to B, he could say, I want to get across the river as fast as I can. So he might choose to row from A to C and then run the 8 kilometers. So this vertical distance is going to be how much he has to run. So we now know the parameters of the problem, but the decision he needs to make is, should he do some other combination? So point D is here to just show one other possibility. Point D could be on a slider. So point D could move anywhere from C to B. So his other option would be to row from point A to point D somewhere downstream, and then he would have to run this remaining distance. So some combination of rowing and running. Perhaps he could row the entire distance and do no running at all. So we've got some options here. So we need to start with a variable somewhere. And since we're already given this diagram, let's let x be the distance downstream, because that's actually the question. How far downstream from point C? How far downstream from point C should he land the boat? So the answer for x could be as much as 8, all right? Or he might row directly across the river. So we know that x is somewhere between 0 and 8 kilometers. So we know our extreme cases. So if x is 0, that means that he rows directly across and then he runs. So he would row the 3 kilometers, the shortest way across the river, and he would run the 8 kilometers. So that's one possibility to get from A to B. And our other option here, this should have been an 8. The other option would be that point X is when he goes directly, when he rows directly from A to B. So y is x equal to 8 because x is the distance below C. So this is the distance that he lands downstream from point C. So this would be if he rows the entire distance, and it would be 0 kilometers of running. Okay, but don't we guess that he's going to do something in between? So now we've got to set up an equation to minimize his time. So I suspect he's going to do some combination of rowing and running. So we need to come up with a formula to minimize his time. Well, let's put a little bit more work now into our diagram. So we're letting this represent any hypotenuse. So if he lands x kilometers downstream, we know the distance across the river is 3. So we see a right triangle. We know that his rowing distance would be the hypotenuse. So his rowing distance is going to be the square root of x squared plus 9, the hypotenuse across the river. And his running distance is going to be whatever is left over from the 8 minus x. So his running distance is going to be 8 minus x. And notice, by the way, that these variables work for the extreme cases as well. So if he rows 3 kilometers across, notice that that hypotenuse will still turn out to be the rowing distance that we want. Okay. All right. So let's set up a function for time. So the time will depend on the length of x. And what we need to add up here is his rowing time plus his running time. And let's be extra careful about this. We know rate times time is distance. So the time is the distance for that portion of the trip divided by the rate. So we know that his rowing distance is the square root of x squared plus 9. And we know that his rowing rate is 6 kilometers per hour. And the time he's going to spend running is the distance he's going to run, the vertical leftover distance. And he can run faster. He can run 8 kilometers per hour. Okay, so now we want to minimize the time. So let me just write t of x in a little bit different format here that you might find easier for differentiating. Let's write this square root as a 1/2 power. And let's split this up into 2 separate terms with a common denominator. So 8 over 8 is 1 minus 1/8 of x. Okay, so this is our formula. Any time, any length of time for any value of x that you would pick. Okay, so what are our critical numbers? Let's find our t prime. So we'll have the 1/6, and then we're going to do a power rule. Bring down the 1/2. And then don't forget that we've got a chain rule here. So we've got to do a 2x. And the derivative of 1 is 0. And the derivative of this term will be a negative 1/8. So this 2 can cancel with that 2. So we've got an x in the numerator of this term and a square root. So here is our derivative. So does it have any critical numbers? Well, we see a denominator. Can this ever be undefined? Well, if we would get 0 in the denominator, or if we'd have a negative under the square root. But neither of those are going to happen. X squared plus 9 is always at least 9 or larger. So we never have to worry about an undefined value. So our only critical number is going to come from when t prime is equal to 0. And that would mean that this first fraction would have to be equal to the 1/8. So let's treat this like a proportion. And you might grab your calculator and do the solver. We could divide this by 2 if you wish. You don't have to, but why not? Makes it easier. To solve, we would square both sides. And let's either distribute or don't, but one or the other. All right, so now we have a 9x squared. Let's bring that to the other side. And we have an 81. So x squared is 81 over 7. So x could algebraically be positive or negative. Square root of 81 is 9. Square root of 7 is square root of 7. We would have plus or minus, but here x is the distance. Remember what x is? X is the distance from C where he landed the boat. So if he rows and runs, so remember that 8 minus x was the distance he was running. Okay, so this is our only critical number. This is our only critical number. And again, if you were running short of time, you might say that's got to be the correct answer. But we don't know whether this critical number produces a minimum or a maximum. So we better do some tests. And remember that the only places that we can get a global extreme is at a closed endpoint or a critical number. So the closed interval test. By the closed interval test, and that would be good enough if you just wrote closed interval test. But remember what it says, global extrema. Global extrema may occur only at critical numbers or closed endpoints. And we had already figured out that we have closed endpoints here of 0. That's if he if he rode straight across the river and then ran the entire 8 kilometers running. So then our x value is 0. In this case, he rode directly across the river and then he ran the 8 kilometers. So x, how far south of C did he land? He landed exactly at C. He rode directly across the river. And our other extreme case was when he rode diagonally from A to B. So then the distance below C that he landed. So then our x value was the entire 8 kilometers. So x could go from 0 to 8. So what we need to find then is our time at the endpoints and our time at the critical number. And you can grab your calculator to plug these in and compare. And if they're not exact values, then change the equal signs to approximates. So put your time function into the calculator, and I'm going to pause and come back and write those. T of 0 turns out to be exactly 1.5 hours. This one we could round to 1.331 hours. And here 1.424 hours. And we wanted to do the minimum. And I've showed you here, as long as you're putting t of x in your calculator, you might want to look at its graph. And sure enough, it does have a minimum value. Right about here is its minimum value. So when x is the square root of 9 over 7. All right, so what do we conclude here? He should land 9 over the square root of 7, or approximately 3.402 kilometers downstream of point C. And that should answer our question.